So, as Professor Uchimoto introduced, I'm Nicolas Mary. I'm working in two labs, MatéIS lab, which is a material science lab at INSA Lyon, and also EliteMax, which is an international joint unit between CNRS, Tohoku University, and Université de Lyon. So, my talk are divided in three parts, subdivided in four actually, and for this I will just make some brief introduction of damage and degradation, and I'm working mostly in corrosion, so we will take to talk about corrosion. So maybe some students from INSA Lyon already knows about corrosion, so I should ask a lot of questions because I know very well their teacher. So let's have a look on the introduction of damage and degradations. So if I just ask you what is corrosion, usually what you are thinking is that chain, boat, pipes, garden entrance, and sometimes reinforced bar in concrete. Often when you talk about corrosion with friends, which are not specialist scientists, they have all the solution. You can paint, and that's it. So corrosion is not only painting when you can see rust, it is also understanding how it will degrade, try to solve degradation, and try to mitigate the degradation. So that's the goals of the other talks that I will give during this intensive course. Sorry. So just to know, the last picture, which is, I think I can I use my, oh, okay, this one. This one has been took 2 days before in Matsushima. You see, guys are taking a picture of boats, and I'm always looking for corrosion pieces. Okay, just before, Professor Uchimoto asked you what is risk management and risk, and what is safety. So I could do exactly the same, asking what is corrosion. And if you look about corrosion, you will find a lot of definitions. Sometimes some of them are from standards, the others are proposed by guys. But if you look if you read carefully, you will find common words. The first one is related to damage. It can be deterioration, degradation, destruction, attack. So you are losing matter. The second word that you will find is always environment. That means the material itself, it's safe. But against environment, it will change. And the second one is, okay, if you have the material, you have the environment, if they are not connected together, you will have nothing, so you need interaction. So usually what we call corrosion is the definition which is given here. It is basically the result of interaction between materials and their environment. Consequently, what you will get is a material loss. So it can be loss of properties. They can be mechanical, physical, chemical. And all this loss of properties will finally goes to failure. So what we have to keep in mind is the picture that I just showed you before. Corrosion is visible, but you can find also corrosion which is not visible. So because you will have almost no weight change of your material, but you can have change in mechanical properties. Today there is a typical example of this kind of degradation. In which kind of environment would we have this modification of physical, mechanical parameters without see that the pieces is changing? Do you have an idea? hydrogen. Hydrogen is a small atom. It will diffuse, but it will change a lot the mechanical properties of the material without changing the general shape of your material. So in this case, only by visualization of the pieces, you will not be able to see, okay, there is rust. We should paint. No. So we have to find new technologies to detect these degradations or this effect of environmental action on the material. Corrosion is also a natural process. It's kind of cycle of life of your material. So in the industries, you start by extract from earth oxide, ores. From this mining, you will apply metallurgical processing. So you will create metals. From metals, you will create infrastructures. This can be a plane, it can be what you want. But if you think about the thermodynamical cycle, oxide and ores were stable, so the energy was minimal. By extracting and by shaping the materials, you change the energy. So what want to do the system? Minimize its energy again. So one way is corrosion. There is also other ways, but for right now, I will just focus my talk on corrosion. So you are minimizing your energy by degradation, and what you get when you corrode materials, you get oxides. Okay, and the cycle is closed. Okay. So now, when we look on corrosion issues, we have 3 questions to ask and try to solve. The first one is, we said that corrosion is because it's by an environment. All the environment are corrosive, but not all at the same degree. Okay. Going to find an example. Salt in seawater is more degradative than a water with a small quantity of salt, for example, in a lake compared to an ocean. The point is, if I'm looking on corrosion, I will looking on metals. So there is a lot of papers dealing with other materials and saying that they are submitted to corrosion. They are submitted to degradation. Corrosion is mostly applied for metals. They can be ferrous or non-ferrous materials. Okay, so if you think about the chemical table of elements, this is the block D. And the third question is, okay, it's corroding, but how it's corroding? What is the shape of the corrosion? What is the morphology of the corrosion? What is the location of the corrosion? When you start to answer to this question, you start to describe the process of corrosion. So you start to understand how your material interact with the environment. So all the materials are sensitive to degradation, that I was saying. And for example, for non-ferrous materials, they are corroding, but they are not rust. Rust is only limited for iron. Usually, we said that plastic are corroding. No, they are swelling, they cracks. Wood, split or decay. Portland cement, leach away. So there is kind of a tricky small definition that may differ from each material. Okay. Consequence of corrosion. So there is corrosion everywhere. The intensity of corrosion can depend about the environment. What we can see. First point is when you detect corrosion in a plant, you will have a shutdown of the plant. So your industry will have some troubles, your customer too. Corrosion can lead to linking from container, storage place, tank. So in this case, you will have a loss of product and you can introduce a more severe accident. This is a consequence of leakage. I may discuss a little bit that. Because of corrosion, you will have a loss of efficiency. So for example, if you insulate a heat exchanger and corrosion starts, you will get a clogging of your heat exchanger. So the exchange will, the thermodynamic equation of exchange, the heating exchange will change and you will have a loss of efficiency. You can get also contamination. So corrosion starts in a piping system, and for example, in pharmaceutical application, you can get some pollution and you lose your production. And there is also sometimes in regarding nuclear transportation of radioactive corrosion product that you have to constrain in for a certain time. Okay. The magnitude of corrosion depends on the metals and alloys and the specific environment. You have to understand this is a couples, and you have to look on a whole system. Okay. So for example, copper is well known as a water pipes. In most of house, we have copper pipes. Unfortunately, if you use that in ammonia, so it has been used, they try to use it 20, 30, 50 years ago because it can be used for the ammonia storage and transportation, and actually ammonia degrades very fast coppers. Okay. So the consequence of the corrosion, they will determine the priority of the maintenance activities and how you have to improve your infrastructure. So usually we divide the failure consequence due to corrosion in four categories. The first one is an operational consequence. So the question is, has the failure any direct adverse effect on the operational capability? The second is safety. Does corroded pieces cause an immediate loss of function or secondary damage? So secondary damage is, for example, you have a pipe, there is a hole starting and the water starts to fall and there is some electrical installation below. You can imagine that you have a secondary damage. Non-operational consequences. So this is a kind of example. For example, in the navigation unit, you have some an element start to corrode, but you know that in airplane, everything is in double. So there is consequence of corrosion. One unit is unusable, but hopefully you have a second unit that can still work. And the hidden failure. So this one, it is the way that you increase the risk. Okay, the risk is not immediate, but you will just start to increase risk until a certain moment, or you will have a loss of properties, for example, for your material. So when we say that, it looks like corrosion is very important. Actually, it is, yeah. Because if we look the gross domestic product of, in average, in all countries that have been actually completed a survey from the NAIS, which is a national agency in US for corrosion, and they make some calculation and they realize that the corrosion is 4 to 5% of the GDP of a country. There is some specific areas where the corrosion is quite important, and if we list some of them, it's randomly chosen. For example, in gas and oil transmission pipes, you will find corrosion cost, a strong corrosion cost. If you look in Arabian Gulf countries, you will see that automotive, the lifetime of an automotive is quite small, only 6 months before observing apparition of corrosion. You will have also same in concrete. Almost 95% of the concrete are submitted to corrosion, and 10% of the aircraft maintenance in US, they are here for corrosion remediation. So the cost of corrosion, usually when you look for companies, they are divided in two parts, what we call indirect losses and direct losses. So what are the indirect losses due to corrosion? A loss of efficiency, a loss of production, the over-design, the shutdown, and the product contamination. So what is over-design? Over-design is the fact that because you want to avoid corrosion, you will scale larger your unit. So that means you will pay more your materials to produce. The direct losses, okay, that's really clear. The material cost, I have to replace. The maintenance. The maintenance is here, it's because, for example, there is a wrong choice of materials for corrosion, regarding corrosion, so it will cost maintenance. So this is a maintenance not because you want to control your unit, it's because the choice was not good, and the human power, of course, you have to pay people that are energetic. So as I told you, the corrosion cost strongly differs from the countries. Here you have a few of them. So US, Japan, I would like to find France, but it was not in the survey. So unfortunately, I don't have the value for France, but you can see that according to the part of the industries in the country and the services, you will have differences about the cost of corrosion according to services, industries, and agriculture. Corrosion penetrates all the industries. So in 2016, the NICE international report tried to give a value of $1 billion according to several items. So if you look in US, the highest cost is for drinking water and sewer systems. Everybody knows that in drinking systems and pipes, we have a lot of leakage, even in France, and we have to fight with that. The motor vehicles was one also of the highest cost, and the last one, because the survey came from US, defense. So in army, they have a lot of problems of corrosion they have to solve. Okay, here this is the kind of list that what the corrosion affect. So the corrosion, when you look for to protect against corrosion, so you have to think about impermeability of the system. Actually, if corrosion starts, you should not have any contamination, so that's we call minimize the possibility of corrosion. Corrosion will modify the mechanical properties, so that means that if any corrosion starts, the mechanical strength, you have to keep at the initial one. Corrosion can also change the dimensional integrity because corrosion is a loss of matter. So you reduce also you change the dimension of your pieces, physical properties, and the other have been already listed. Okay. So now, who is studying corrosion? That's a good question. The first one are the scientists. Okay, why they want to study corrosion? If you are going to a do-it-yourself shop, you will find painting and that's it. No, it's because we want to improve the understanding of the cause of the corrosion. We want also to find ways to prevent or minimize damage caused by corrosion. The second point is very important because today you know that we have to take care of the materials and the structures that we already built. So we have to maintain our actual structures. And to maintain actual structures, that means that we have to prevent them to corrosion. And what are doing corrosion engineers? For them, they try to apply the knowledge to control corrosion. So there is here a small example. That's for piping system, for example. So in a pipes, there is a well-known technique, I would say cheap. It's a cathodic prevention. Cathodic protection is quite easy to understand. You just apply a potential to your pipe and you protect. So that's the corrosion engineer will apply. But what will do the corrosion scientist? He will test and develop new protective coatings. So painting, corrosion inhibitors, coatings, what you want. Actually, when you work in corrosions and when you look corrosion, you need to have both viewpoints because usually you need to understand the damage, the origin of the damage. You need to have ideas about what kind of remediation you need to test your solution. And after, if the solution is good, you can apply it. Another job from the corrosion engineer is to apply his knowledge in this pyramid of management element. So I will not go too much deeper in this. It is just because you see there is a classical management system element, which is in dark blue. That's usually what we can find in companies, and you will see also that here you will find risk management, management review, incident investigation, and so what we have to do with corrosion is to add based on the pyramid, which are here. So we know that our structure or infrastructure can be submitted to corrosion. So we have to look for procedure to evaluate the risk. So it means inspection. If a lot of questions about inspection, I should know which kind of risk of corrosion that I have to select the best inspection method to evaluate any damage. So that means I have to select an inspection method where I can implement this inspection method. That's also another question. In a pipe, should I put this in a line part or in the elbow part? And of course, how can I mitigate the problem of corrosion? And when I have that, I can make some plans, and because I have an idea about the corrosion type, life cycle of the material, and so on. So it's make like a plan of maintenance or plan of inspection. So one point is usually materials are designed by persons from the mechanics part. Mechanics is equations. They are not taking into account environment. And we said that environment is important. So that means that nowadays, most of mechanical engineer knows about degradation as corrosion. That means that they have to think when they design a structure, the process and they build the equipment, they have to think about what kind of corrosion, what kind of degradation, not only mechanical, chemical also, will appear. So either they design, either they bought from another company, you operate, and from the operation is, okay, what kind of strategy for the maintenance, when I should update the materials. So that means that I know that regularly I will need to stop my business unit and replace some pieces. And also, what can I do with the failed parts? If you are working in pharmaceutical environment, so that means your pipe has been polluted from chemicals. Okay, can I release it or not? And so on. Taking this is very important because you have to find a compromise between I'm trying to get the zero risk, and we know that doesn't exist, but trying to reach this goal, it will cost a lot, indirect cost, but also direct cost. And another solution, which could be, I don't care, let's see what's happened. So that's not good because here you have in this scheme, here this is a prevention. So in this, on the left, you are in a high prevention. So this is the green curve. High prevention costs a lot. Low prevention doesn't cost anything. The problem is, at the opposite, if you don't care about preventive correction, the corrective correction will cost a lot. Instead of to put some rubber tip on your tire for your bicycle, for example, you will have to change the tire, the entire tire. So it costs more. So one of the highest difficulty here is to reach this minimize. So you will always convince scientists, but that's not the guy that you have to convince. Actually, this is a financial manager that you have to convince. He has to put money on effort to prevent degradation, which for him is a cost, a direct cost, which he wants to avoid. So I will not go in detail and in this table because this table has been already introduced by Uchimoto Sensei. Actually, is how to evaluate the risk of degradation. So you have the probability of the risk. So the probability of the risk is a corrosion-related failure for us. So you see, we just apply the same methodologies that for mechanics. And the consequences of the risk. So that means that here, you need to understand what is corrosion, what is the consequence of corrosion. This means also that you need to fully understand what is the infrastructure. What is your infrastructure? What are the consequences of loss of properties on your infrastructure? I'm still on time? I don't know. How many time? Okay. Thank you. Okay. If I want to enroll you in corrosion studies, I will use this slide. It's why we should study corrosion, and there is 5 good reasons for that. The first one is material resource consumption. We have a shortage of some materials, rare materials, for example, and they are used to produce alloys, stainless steel, chromium, molybdenum, nickel. We know that the resources are not infinite. So if they are not infinite, that means the product that we have made, we need to save it in time. So we have to avoid corrosion. The good point is even corrosion has start from sinteries. We don't know all the corrosion history for materials. So we have an incomplete knowledge of that. So we need to update our knowledge. And why we need to update our knowledge? Because the environment becomes more and more aggressive. Atmospheric environment has been changed from the Middle Age to now. So corrosion mechanisms have changed a lot also. As shown by Yoshimoto Sensei on this first slide, there is important and very severe disaster due to corrosion. Okay, it's a good occasion to. One very important point now is, okay, so we need to have a hip replacement. We have a lot of surgery, so we need to design materials that can fit with human's body. And in human's body, there is also corrosion. And also corrosion is a threat to the environment. Okay. So better corrosion management. If I want to correctly manage infrastructure, I need to know the cost of the corrosion, the potential saving. What can I do for corrosion? When can I promote corrosion management in policies? That's important actually. This one is quite tricky, so that's why we are trying to teach a bit about corrosion. As it is a degradation at the end of the use, not at the beginning when we design. So we need also to educate and train staff about corrosion. And of course, we need to develop advanced corrosion control technologies. So that was quite general, but now let's have a look on corrosion is what at the end. So in corrosion, there is, let's say, 3 environments. High temperature environments, atmospheric environment, and aqueous environment. The difference is what? High temperature environment, usually it's because the environment is a gas, and the temperature is, so there is always a question about what is the limit of temperature, but a couple of 100 degrees. Okay? And there is a specific mechanisms of degradation. I will talk in another, I will give some information about that in another talk. Atmospheric environment, this is the one that we are facing each day. It's because you have evolution of humidity, you have evolution of temperature, you have evolution of pressure, you have evolution of pollution. Okay, this is the atmospheric. The third one is aqueous. So aqueous is quite easy. It is in water. That's the electrolyte. This is the solution. And if you look for the water, corrosion in water, sorry. If you look on that, we are able to divide corrosion in 8 general types of corrosion. So that means that if you look at the pieces, it will have a shape looking as uniform corrosion or intergranular corrosion. So you see intergranular corrosion, we start to implement the corrosion mechanisms with the metallurgy of the material, with the microstructure of the material. Galvanic corrosion, crevasse corrosion, pitting, erosion, stress corrosion, cracking, biology. If we look on that, there is some corrosion that are, let's say, from the material, and some of them are because material is not only alone as crevasse corrosion, galvanic corrosion, or is also influenced by the environment. Erosion, corrosion. That means that the material is submitted to a flow of water, particles, stress, corrosion, cracking, stress. That means that we are applying a stress, mechanical stress on the material, and it's not only in a friendly environment. And biological, you understand, this one is mostly for human body, but not only. Okay. Usually, we can find, let's say, summarize kind of material systems that are submitted to this kind of type of corrosion. There is some driving force, what we have to control, and some remark. I will just detail this table a little bit after. This is just to give some example. Just to give you an idea, because this is the hate, but okay, what kind of corrosion we can find the most? Actually, the largest one is corrosion fatigue. What is meaning? That means that you have a material submitted to a fatigue, mechanical solicitation, loading, which is a fatigue, plus corrosion. Okay, spring for your car, for example, is one of the examples, but not only. Bridge cable could be also. General corrosion, so that's the largest one. And if you remember the few examples that I chose at the slide, sorry, the most of them were general corrosion. So there is a little bit of high temperature, and after others are mostly divided in the same value. One point. At the time where the graph was done, the hydrogen embrittlement was only 1%. And most of the hydrogen embrittlement come from oil and gas industries. But nowadays, with the evolution of hydrogen energy, we are expecting that hydrogen embrittlement will increase. So what is hydrogen embrittlement? For those who don't know, it's the consequence of hydrogen penetration, diffusion, trapping in the material, and changing the mechanical properties of the material. So you will have a brittle failure of your material, for example, instead of to have a ductile one. Okay. If I try just to summarize a little bit the driving force, corrosion is driven by thermodynamics. Okay, so in thermodynamics, what we have as a parameter, temperature. Okay, this is one. Corrosion is also driven by potential. The potential is also a thermodynamical quantity. The potential can be tuned using ions in solution. So ions, it will be anions, chloride, for example, for the salt in water, or pH. And there is also another potential, which is gas. Okay. I'm pretty sure that you will remember your class of thermodynamics in first or second year, for those who have done engineering school. Okay. That's for the environment. So you can have a look rapidly everywhere. You will find at least one of these parameters who have a strongest effect than the other one. Regarding the material, if we look on material, we always have the same microstructure heterogeneities. Okay, until now, it costs a lot to create monocrystal of materials. Should be interesting for mechanical properties. I don't know. I don't come from the mechanics. But from the corrosion viewpoint, yes, it will be. If I have a monocrystal without any defect, starts to be very good. So that means that the microstructure itself of the material will act on, on its degradation regarding corrosion. So it can be defect, void, inclusion, heterogeneities, but also grain boundaries. Because you know that in the materials, all the grains don't have exactly the same crystallographic orientation. A crystallographic orientation is what? Is plane of atoms with different densities. Which mean densities? It means different surface energy. Energy, thermodynamic, we restart. Okay, so everything is linked. In terms of energy, we have also residual stresses. So that's the first point. And its chemical composition also. I have a funny story about the chemical composition. I have time? Yes, okay. So a couple of years ago, I've been involved in expertise about surgical scissors, okay? So previously, the hospital had a very good surgical scissors, and they need to be replaced. Frequently, they have to change for biological viewpoints. So at that time, the management, the financial management was not driven anymore by a surgerist. It was done by someone who has done a business management school. So in France, what we have, what we call appel d'offres, which is kind of, you call for companies who can answer. So companies answers, the previous one and new ones. And actually, the financial manager choose the one who proposes the lowest price. Sounds perfect. They receive scissors, surgery, and you know that after each surgery, they are using a very strong basic solution plus other treatment to clean virus and bacteria, okay? After the first cleaning, scissors were fully corroded. Okay. The question was, why? So we make an investigation for them. First question is the scissors are in the regulation? Did they reach the regulation rules? So you know that, or you may not know, but for scissors, chirurgical scissors, they need to have a specific chemical composition. One of the chemical composition which is very important for these scissors is sulfur, because scissors, they are made with iron, chromium, manganese, and sulfur. They had sulfur because it's easier to machining, to design the shape of the scissor. We check. Actually, they were in the rules of chemicals element quantities. The point was they were at the upper limits. That means that compared to the previous scissor, the quantity of sulfur was higher. Okay, but almost at the limit. When you increase the quantity of sulfur in the material, you will create defects, which are well known, which are sulfur. Okay, I have in French magnesium sulfur inclusion. And this sulfur, magnesium sulfur inclusion, they are very sensitive to the cleaning bath. So, because they pay less, they get less quality of scissors, and they corroded directly after the first bath. So the end of the story was they reject the contract with the provider, and they turn to the previous one who has a lower quantity of sulfur and better resistance to corrosion when they clean. Okay, the price difference was because there is less sulfur, so it's more difficult to machine, so it takes more time. It costs more. Okay, this is a kind of example of chemical composition. Okay, how I can recognize corrosion. I like this small draw because it's quite visual to know what's happened. And I will give some picture right after. Usually, we for the 8, no, for more than 8 here, corrosion types, we are using groups. The first one is the group 1 for identifiable by visual inspection. It's cost almost nothing. You just train people and they are going to the infrastructure and they watch. They watch what? Uniform corrosion. So you have a draw here and you can see that, yeah, you will have a depth created. Pitting, so it's a local dissolution of the material. Sometimes it's not so easy to observe, but you can. Crevice corrosion. So crevice corrosion, I will give a small detail about that, but it's clearly when you put a pieces and actually the material will dissolve under the pieces. Or galvanic corrosion, that's a funny type of corrosion I will show you. It's because one material is protected and the other one dissolves. So it's very easy. The second one is with inspection tool. So you will say, why erosion? We can see there is some crater on the surface. Actually, erosion, if you think about a flow, usually it's because you are in a pipe. So it's happened inside the pipe, not outside. So you cannot visualize what is inside the pipe. So you need inspection tool. Cavitation is exactly the same. Freighting, so freighting is a kind of surface mechanical loading where two species are slightly moving together. Intergranular, so here this corrosion type is because you have different grain boundaries and they are not attached anymore. There are no chemical or physical bonding between atoms and you start to detach atoms. And some of them you will need microscopic examination. So you will, for elite school guys, you will have a talk about a microscopic. Yes. So stress corrosion cracking, corrosion fatting, scaling, internal attack. So this is all. I forget the name in English. This is quite important in the case of materials sensitive to hydrogen emprisonment. Actually, hydrogen will diffuse and make some drops of hydrogen in the materials. As it's a gas, the structure starts to increase and you create some gas volume inside the material. Okay. Some detail about corrosion. A beautiful picture from the general corrosion. What we can see. It's a uniform attack. It's mostly at the large scale. Some pieces of the boat are still remaining, but they will be removed. Sometimes general corrosions can be used for architecture or design. Here, for example, so I'm sorry it's in black and white, but here you have a sculpture, and actually the designer is using the natural corrosion because of the microstructure of the material to get some pattern on the surface of the sculpture. Sometimes you would like to avoid general corrosion in a piping system, but sometimes you like corrosion. Here it's a copper roof. With the atmospheric corrosion, you will get some copper oxide, not only oxide, but there is also a mixture with other polluants from the atmosphere. and you can get this beautiful green color of the roof. So it can be also designed. So okay. So I should not enlarge the picture. So for those who still have a very old watch, you can have some pits. So I'm really sorry because the picture is very dirty, but pits, they are here. You see, this is points of defect on the back of your watch. And this is because of what? Because of the humidity of the skin and also about the salt of your skin. Okay. And here, even if it is, for me, it's stainless steel, but stainless steel is quite sensitive to pitting if there is any chloride environment, so Cl minus. And here you will have such kind of degradation for a long-term exposure. So you can see here, not all the structure has been damaged, it's locally damaged. Which is interesting with pits, they can change their morphology. There is a variety of design of pits. So here you have some typical cross-section that has been taken from a literature book. So pits, they can be narrow and deep, shallow and wide. And you see a lot of design. And this design will depend about a lot of parameters: environmental, microstructure, evolution of the chemistry. 2 minutes. Wow. Okay. So I will go fast because after this is only a demonstration. And here it's to show you that it can be quite difficult. Okay, pits and the consequences of corrosion at the pit. You can have information about what was the environment. This is a copper pipe in a piping system. And actually, if you look up about what you have, here it's a degradation, you look on the product that you have, and you can go to the history of the pieces. That's also very interesting. It's kind of expertise. We still, with pits, for example, we still try to develop some models to understand. I told you, we are scientists. We want to know. So we keep on going what happened to understand. Another kind, crevice. It's because there is some water going between two pieces. You change the environment. There is some very specific models here. So you see at the beginning almost nothing, but with the electroneutrality of the solution, you start to have ions diffusion, the ions concentration change, and you change the environment. Material is not safe anymore, and have dissolution. Which is interesting is it can happen everywhere. So you have a beautiful map of cars, and here all the points are where the damage can appear. So you can see that from the picture that the cars are very old. So now there is improvement to protect car bodies from the corrosion. Okay. And I think I will stop right there. This is the one typical corrosion that we can find when designers are not aware about corrosion. It's because they select two materials. Because it's easier to make an infrastructure, so they will take two materials. The problem is the two materials are significantly different potential energies. So that means one will be protected when the other one will dissolve. This is typically the case when you try to make some soldering with coppers and steel wire, for example. In this case, the steel wire will dissolve very fast. Okay. And at the end, for each image, for each case, you will find typical image. So here it's for intergranular. You see, we can see the grains of the materials. Here it's erosion for blades for piping system. Here it's stress corrosion cracking. So it's kind of cracks, a tree of cracks that are going into the material. So you can see the last one. From outside its inspection visualization, you will see nothing. But if you correctly select inspection method, and you can see the size is small, so it's quite tricky to select this method, you will be able to select this. I love this picture. Thank you for your attention.